You have felt it your entire life. The sharp sting of a paper cut, the deep ache of a muscle pushed too far, the strange, hollow pressure in your chest after a loss that had nothing to do with your body at all. Pain is the most universal human experience. Every person alive knows what it feels like, and almost no one understands what it actually is. Because the moment you look closely at pain, really closely, it stops making sense. Tiny cuts hurt more than serious injuries. People finish races on broken legs. Amputees feel agony in limbs that no longer exist. And the brain, for reasons science is still working to fully explain, can generate genuine, debilitating pain when the body has not been damaged at all. Pain is real, always, but the relationship between pain and injury is far stranger and far more interesting than most of us were ever told. For most of human history, the explanation was simple. Damage the body, signals travel to the brain, you feel pain. The body as a telegraph wire, sending messages upward. The brain as a passive receiver, reading what arrived. That model felt logical. It was intuitive, and for a long time, it dominated medicine. Then came the war. During the Second World War, an American surgeon named Henry Beecher worked. He noticed something that didn't fit. Soldiers arriving with catastrophic injuries, shattered limbs, massive wounds, damage that would completely overwhelm a person in any civilian context, were often calm, alert, reporting little or no pain. Some declined morphine entirely. Beecher was careful and methodical. He documented it systematically. And when he published his observations in 1946, medicine had no satisfying explanation. The injuries were severe. The pain was absent. How could that be? Until 1965, when two scientists, Ronald Melzack at McGill University and Patrick Wall at University College London, published a paper in Science that shifted the entire field. They called it the gate control theory of pain. Their proposal was radical for its time. Pain signals generated in the body do not travel directly to the brain. They pass first through the spinal cord, where neural circuitry acts as a kind of gate, regulating how much of that signal is allowed to continue upward. The gate can be opened, allowing more signal through, or it can be partially closed, reducing what the brain receives. And critically, the brain itself sends signals downward that influence how the gate behaves. This single idea explained so much that had previously been mysterious. Rubbing an injured area generates competing sensory signals that can partially reduce the flow of pain signals through the same pathway. Fear and anxiety can prime the system toward heightened sensitivity. And the extreme focus and adrenaline of combat can activate descending pathways that powerfully suppress incoming pain signals. Gate control theory was revolutionary. It proved that the relationship between injury and pain was not fixed and mechanical. It was dynamic, modifiable, and profoundly influenced by the state of the nervous system itself. That insight has implications that reach far beyond the battlefield. Consider the athlete who plays through an injury, the footballer who walks off a field with a fracture he didn't know he had, the climber who only notices the severity of a wound after the immediate danger has passed. In high-intensity, high-stakes situations, the brain's descending modulation systems can dramatically reduce the pain experience, allowing the body to continue functioning even when tissue is genuinely damaged. But this raises something even more unsettling. If the brain can suppress pain when damage is present, what does it mean when pain is present when damage is not? Fibromyalgia involves widespread pain across the body with no identifiable structural damage to explain it. Neuropathic pain can persist for years after a wound has completely healed. The the nervous system continuing to generate signals long after the original cause has resolved. Migraine produces debilitating pain through mechanisms that researchers are still actively working to understand. Which brings us to a story that makes all of this suddenly very personal. After amputation, a significant proportion of patients, studies suggest between 60 and 80%, experience sensations in the limb that is no longer there. A hand that no longer exists cramps into a fist that cannot open. A foot that was lost years ago burns as though pressed against heat. Fingers that are not there ache with an intensity that disrupts sleep. This is phantom limb pain, and it is entirely real. It emerges from a combination of factors that researchers have been working to disentangle. It persists, it reorganizes, and in many cases, it continues to generate activity associated with a part of the body that can no longer send signals upward. The brain, in a sense, is trying to account for a territory it no longer has access to. Phantom limb pain is one of the clearest demonstrations we have that pain is not located where it feels like it is. It is an experience produced by the nervous system, shaped by the body, by the spinal cord, and ultimately by the brain. And it reveals something profound about what pain actually is. Pain has no single location in the brain. The thalamus routes incoming information. The somatosensory cortex processes the location and quality of a sensation. The anterior cingulate cortex is involved in the suffering dimension, the emotional weight that makes pain not just a sensation, but an experience. And the prefrontal cortex is involved in interpreting meaning, context, and what this pain might require you to do. Each region contributes something different. Together, they produce what we call pain. And here is something that research has consistently found, and that is worth sitting with. The anterior cingulate cortex, deeply involved in the suffering component of pain, shows overlapping activation during social rejection, grief, and experiences of loss. When people describe emotional loss as feeling like a physical wound, they are not speaking loosely. They are describing something that imaging studies have repeatedly suggested, that the brain processes certain forms of social and emotional suffering through some of the same systems involved in physical pain. This finding has implications that reach into almost every part of human life: loneliness, grief, exclusion, heartbreak. The brain does not treat these as purely abstract experiences, which makes what happens next even more remarkable. In carefully controlled clinical trials, patients given inert substances, told they were receiving effective pain relief, frequently show genuine, measurable reduction in pain.
This is the placebo effect, and it is not evidence that their pain was not real. It is evidence that the expectation of relief can activate the brain's own endogenous pain modulation systems, releasing opioids, altering signal processing, genuinely changing what reaches conscious experience. Conversely, and this is harder to hear, negative expectations can do the opposite. When patients are told that a procedure will be painful, they tend to report more pain than patients given the same procedure with neutral framing. This is the nocebo effect, and it demonstrates that the nervous system is not simply responding to what is happening.
It is also responding to what it anticipates. One influential modern framework in neuroscience, predictive processing, proposes that the brain is constantly generating predictions about the state of the body, comparing those predictions to incoming signals, and updating its model of what is happening. In this framework, pain is understood as a protective output, something the brain generates when it predicts that the body may be in danger and that action is needed to prevent further harm. There are people who have never felt pain, not because they are unusually resilient, because a rare genetic condition called congenital insensitivity to pain prevents their nervous system from generating the pain experience at all. For a moment, this might sound like an advantage. It is not.
People with this condition sustain injuries they cannot detect. They develop joint damage from repeated stress they never receive the signal to avoid. They sustain burns without awareness. They experience fractures without knowing. And many of those affected do not live to old age. Pain, as uncomfortable, as unwelcome, as disabling as it can be, is one of the nervous system's most essential survival tools. Every time it has pulled your hand from heat, caused you to favor an injured limb, woken you in the night with a warning, it was doing something remarkable. It was trying to keep you intact. Pain is ultimately a protective experience generated by the nervous system, shaped by signals from the body, processed through the spinal cord, and produced as an output by the brain when it assesses that protection is needed. It is real, it is complex, and it is far more than a simple alarm. The same system that generates a paper-cut sting generates the suffering of grief. The same network that warns you away from fire can generate pain in a limb that no longer exists. And the same brain that produces all of this is also the brain that wonders about it, that reflects, that questions, that asks why. Science has made extraordinary progress in understanding pain over the last century. But the deeper we look, the more clearly we see how much remains to be understood. Perhaps the most honest thing that can be said is this: your nervous system has been working on your behalf every moment of your life, generating experiences designed to protect you, using mechanisms you were never aware of, calibrated by everything you have learned, felt, and survived. And if that much has been happening beneath the surface of your awareness, what else might your mind be doing that you have not yet thought to ask about? If you're curious about how your mind and our world really works, subscribe to Why Decoded. Because everything has a reason. We just haven't decoded all of them yet.